Hi students, this is Sumit Kundu here, and today I'll be taking up a session on thermal physics, my dear students. Okay, uh, just giving you a short intro about myself. My name is Sumit Kundu, and I've done my BTech from IIT Bombay, passed out in the year 2007. And since then, I worked for the corporate sector for a couple of years. And from 2011, I have been teaching physics to JEE aspirants as well as medical aspirant students. Okay. And students, it's been a beautiful journey seeing so many bright child passing out every year under my guidance through these competitive examinations. And here I'm with you guys today teaching you thermal physics. Okay, now regarding thermal physics, let me tell you it's supposed to be one of the picnic time for the students. Okay, primarily because of the fact that after the hard grinding sessions of mechanics that you have had, and just lately you must have done rotational mechanics. Okay, and all those things, thermal physics is a welcoming treat for all the students. Questions are easily solvable, formula based, and students enjoy this part. Okay, now students, going ahead, let me just explain to you how have I designed this particular module out here. Now I have taken two sections. Now as such, if you see thermal physics, or let's say heat and thermodynamics, which is usually been referred to in most of the books out here. Now, heat is the part we tend to cover in 11th, all right, and thermodynamics is the part we tend to cover in 12th standard, okay. Now, if you look at it broadly, we have the concept of heat, the basic concept of heat as the dealing with temperature and what is its different scales, and you actually kind of measure them. All right, and then we come to thermometry. All right, so these are all dealt with about the basics of heat. Then we look at a topic called as calorimetry. Calorimetry. All right, and then we go to something called as thermal expansion. And then we have heat transfer. And after that, we have got something called as kinetic theory of gases. We will abbreviate it as KTG, kinetic theory of gases. And then finally, we have got laws of thermodynamics. All right. So overall, this is the roadmap which we have for your entire thermal physics, my dear students. Okay. Now, among these, just give me a second. Among these, what we see, the part that we are going to cover out here in today's session, my dear students, is going to be thermal physics and a bit of heat transfer. Okay, so these are like very basics. Heat and calorimetry are like very basic. So applications of thermal physics is what I have looked at, few examples from there. And the second thing that we are doing is going to be on heat transfer. Just the basics of it. We have taken heat transfer could be taken place by multiple modes. Let's say we have got conduction, convection, and radiation. So we'll be dealing with only the part that is called as your conduction. All right, students. Now, thermal expansion, the basics of thermal expansions you have been exposed to even in junior classes. All right. We all know, when you heat a metallic object, it expands. It could, go ahead and expand in either length or in area or in volume. Okay. Now, typically, what is the reason behind this expansion to actually take place? Okay, let me just explain to you in a brief. Say we have a conductor. Now we know, students, inside a conductor we've got like many molecules. Okay, so these are the molecules inside the conductor, and as such they have some energy and they vibrate about their mean position. So they would probably be like, vibrating this way and this way, or this way and this way, this way and this way. So right now they are vibrating only in this particular zone. Okay, so this first molecule would be vibrating between this point and this point out. Now when you started providing it heat, my dear students, what happens? These molecules are going to get more heat. All right, and as they kind of get more heat, they are going to vibrate even faster, and they would require more space to vibrate. Okay, so technically talking, what is going to happen is these molecules now require greater region. Probably it is going to vibrate in this zone. This molecule is going to vibrate in this zone. This one is going to vibrate in this zone. So the region that these molecules require in order to vibrate, that has to be increased due to its increased energy. As a result of which, what is happening, my dear students? The length of the conductor is forced to increase via a particular length, call it as delta L. Delta L, students out here, it's nothing but it is the change in the length which has taken place. Why? Due to the process of heating. So this is taking place due to heating. Okay. So my dear students, the same thing happens in terms of area, and the same thing happens in terms of volume. So this is the basic reason why you would see that a solid, okay, as such a solid like a gas, the molecules cannot freely move about. So they are at their position and they are kind of vibrating about the mean position. Okay, so this is the reason that they go ahead to expand. All right, students. Now, here I'll be taking up one slide and explain to you very basics, the formulas that we are going to be using. Students, we know that the fractional change in the length is proportional to the change in temperature, delta T. Okay. So here, removing the proportionality sign, we are going to get delta L upon L is going to be equal to, my dear students, nothing but alpha times delta T, which implies my delta L, which is nothing but my L1 minus L is equal to L times alpha into delta T, which is going to give me L1 as equal to L times 1 plus alpha delta T. So students, here this is what is my basic formula that I'm going to be using for most of the questions. Okay, so this is nothing but the new length of the conductor, and this was the original length. Okay, so this is the original length, this is the new length. Here, this term, my dear students, which is called as your alpha, it is called as the coefficient of linear expansion. Coefficient of linear expansion. All right. And students, the value of this coefficient of linear expansion is of the order of 10 to the power minus 5. So it has got a very small value. So as such, if you see the change in length is very less for a given a small rise in temperature. For 5 degree, 10-degree rise in temperature, you would see the length is not increased appreciably. All right. However, for much higher rise in temperature, you're going to see some appreciable length change. All right. Now, students, the same kind of a formula is applicable for your area. So you're going to see that, like, the new area A1 is equals to A into 1 plus beta delta T. And similarly, you will see the new volume will be equal to V into 1 plus gamma delta T. And through suitable derivations, we see a relation, that is, my alpha is to beta is to gamma is equal to 1 is to 2 is to 3. So there's a relation between a material's coefficient of linear expansion, coefficient of superficial expansion, and coefficient of volume expansion. Okay, so if it is increasing in area, my dear students, we call it area expansion, or also we call it as your superficial expansion. All right, students. Okay, great. So this is, for this we have alpha, for this we have got beta, for this we have got gamma. For this, the application, this length is L into 1 plus alpha delta T. For the case of area, it is going to be A1 is equals to A into 1 plus beta delta T. And for volume, it is going to be equals to V1 is equals to V into 1 plus gamma delta T. All right. So these are the three most important formulas that we'll be looking at, and most of the questions are going to be solved using only these three formulas. All right. So let's go ahead and look at my first question based on thermal expansion. Now here, students, I have got a case. So all of you ready? All geared up? Great. So here I have got a rod. It's got a length of 1 meter. So this has got a length of 1 meter and its mass is 1 kg, and it is placed on a smooth horizontal surface, and the temperature changes by, excuse me, excuse me. The temperature changes by 10 degrees centigrade, and value of alpha is 10 to the power minus 5. So they have asked us what is going to be the change in the length. Okay, I think that's a very simple one, isn't it? So here, if I kind of, let me take it from this page only instead of going to a new one. So we're going to do the first problem here, find the change in length. So we have studied just some time back that delta L is equal to L into alpha delta T. One simple formula, okay, which is going to give me L, that is the original length, 1 meter, into alpha, 10 to the power minus 5, into delta T, that is like 10. So this is going to give me 10 to the power minus 4 meters as the change in the length. Okay, so students, this is a very easy problem, the first one. The second one is also kind of easy. Okay, they are saying if the rod is kept vertical, find the work done by gravity and the distance moved by the center of mass. So work done by the gravity is going to be nothing but the mg force into the distance moved by the center of mass. So the first thing that we are going to look at, by how much distance is the center of mass going to move up. Okay, now let us just have a quick solution to that. Say this was the horizontal surface on which this block was kept. So let's say this is the block initially, okay, and this is where the center of mass is lying. So if, let's say, this length is L, then students, what is going to be the y coordinate of the center of mass? call it as my y1, let's say. So students, if this is like my origin here, so y1 we know is going to be L by 2. Now you provide this rod some heat. Now on the application, that when it starts to get heat, it is going to expand in its length. Now what happens when it expands in length? Let's say it kind of goes up to this much. Okay, so this is like my new length. So is the center of mass going to be here now? Obviously not. The center of mass also has risen up. So let's say now the center of mass is somewhere out here. Okay, so the new location of the center of mass is somewhere out here. And call it this position as your y2. So students, what is going to be y2? Let us just understand that. By how much has the particular rod moved up? It is moved up by a distance. I can call it as your delta L. All right, so this new length is right now L plus delta L. Clear, students? Now the new length is like L plus delta L. So what is going to be the coordinates of y2? That is the location of the new center of mass. It is going to be equals to L plus delta L divided by 2. L plus delta L divided by 2. So by how much is the center of mass moved up? The center of mass is moved up by delta y, which is given as y2 minus y1, students. So that is going to be L plus delta L by 2 minus L by 2. So that is going to be like delta L divided by 2. So this is the distance by which the center of mass moves up. To certain extent, some of the students, what they do is, if like the rod expands by delta L, the center of mass is also gone up by delta L. But rather that's not the case. If it expands by delta L, the center of mass is going to go up by delta L by 2. So this is a point that is worth remembering. Okay, fine. And then it asks us what is going to be the work done by gravity. I think that is pretty simple now. So the work done by the gravity is going to be minus mg into delta y. All right, if you look at the values out here, what is mass? Mass is equals to 1 kg. Take it here. 1 into 10 into delta y. Delta y is delta L by 2. From the previous slide, we see delta L is nothing but 10 to the power minus 4. So we put the value 10 to the power minus 4 divided by 2. So it is like minus 5 into 10 to the power minus 4 joules. This is the work done by the gravity for the center of mass to move up by delta y. I hope everyone has understood this particular problem here. Very simple application of expansion. Students, let's go to the next problem here. Okay, so what do we have in the next problem? Let's have a look. Wow, this is one of the very standard problems which are there in your expansion of solids. I've got a metallic plate here. Now, in this metallic plate, I have got two holes in which the diameters are defined as like D1, and here the diameter is going to be defined as your D2. All right. So D1 is the diameter here, D2 is the diameter here. They are asking us if I start providing heat to this metallic plate, what is going to happen to the diameter of two holes? Now there are someone I would say both of them are going to remain the same. Other people would say that D1 is going to increase, D2 is going to remain the same, or D2 is going to decrease. So there are multiple combinations. Okay. However, there is one good way of looking at this entire thing. This is just like this. All right. It is pretty simple. Just what is going to happen is a photographic enlargement. Okay. You've got a passport size photograph and you've got a full blown photograph out here. So definitely the size of your eyes are going to increase in the full blown photograph as compared to the size of your eyes in a passport size photograph. So this is exactly what happens. So here my D1 is also going to increase. and also my d2 is also going to increase. All right. So this is a simple, I would say, a concept problem for your thermal physics expansion based. Okay. Now here we take up another problem. Pretty interesting, this one. Okay. Village areas, you have seen that there are bullock carts, and on these bullock carts, they have got the internal structure of made up of some metal, and they place a wheel over it. And generally, students, the wheel, this is the wheel out here, the size of the wheel is made a little smaller than the size of the entire rim, the metallic rim which is there. Okay. The reason behind that is what they do is they kind of heat up the wheel, so it kind of increases in its dimensions, and then they go ahead to put it on the rim out here while this tire is still hot. Okay. And then what happens is like, so this is like, the metallic wheel that you have out here, and probably this could be wooden also, or it could be like, metallic as well, probably, or just keep it as like, your wooden rim that is out here. So the metallic wheel goes on top of this particular rim and it cools down. It fits pretty nicely onto the rim. Okay. So this is the entire idea out here. So in order to make it fit, you expand it and then fit it. It cools, it fits, consolidated. Okay. So here they have asked us, there is an iron tire. It is to be fitted on a wooden wheel. Okay. So we have this as my wooden wheel. Okay. And the diameter of the tire is 6 millimeter smaller than that of the wheel. Okay. So they have told us the diameter of the wooden wheel is like 1 meter, so that is equivalent to your 1000 millimeter. All right. And here the diameter of the tire is like 6 millimeter smaller than that of the wheel. Okay, students. So what is the diameter? Very simple, 994 millimeter. They want us to find the temperature by which the tire must be heated, okay, so that it can easily fit into it. All right, and they have given us the value of your beta, which is equals to 2.4 into 10 to the power minus 5. Okay, students. Now here I know the area is given as pi r square. Clear? Students, the first part you're going to do is find out dA. What is going to be your dA? 2 pi differentiation, 2 pi r into dr. Okay, so this is what I'm going to get, 2 pi r into dr. Also, we have seen the change in length, or the formula that we had here. Okay, or let's say we had it here. All right, from this formula here, I can say, let me go back here. Oh, no, sorry, here. That is A1 is equals to A plus A beta delta T. Then students, A1 minus A, which is nothing but the change in area, could be written as A into beta into D delta T, which implies your dA could also be written as A beta into dt. If there is a small change in temperature, the change in area is going to be very, very small. And here, applying differentiation to this area of the wooden wheel, we see how is it linked to the radius of the wheel out here. So this equation gives me the relation between the change in area and the change in the radius, and this gives me the relation between change in area with respect to that of the temperature. Okay. So from equation 1 and 2, my dear students, what we can do very simply equate 1 to 2. So we get 2 pi r into dr is equals to A into B, all right, beta into dt. Clear? And from here, we would like to know how to find out the temperature. Okay. Now here, my dear students, what is this? This is the original area. So this is like pi r square. So I can write 2 pi r dr is equals to pi r square that we had taken out here into beta into dt. So pi is going to cancel, 1r and 1r is going to cancel, which is going to give me nothing but 2 times dr by r is equals to beta dt. Clear? So students, we can now go ahead, solve this problem out here. Integrate both sides. All right. They want us the temperature, find the temperature by which the tire must be heated. So that is like nothing but your delta T. Okay. What we can do is we can avoid all this integration as well, because they have asked us right away what is your delta T. So what you can do, instead of doing all this, you could have gone ahead with this, or what I can right away do is, my dear students, 2 pi r into delta r is equal to pi r square beta into delta t. What have they asked us, students? They have actually asked us to find out your delta t. Made your life simple by removing all that integration. Good. Chalo. So what we can do here is now 1r and 1r will go away. Okay. So delta t is going to be equal to pi goes away, 2 times delta r divided by r into beta. Okay. Students, if you see here the values to delta r, what is going to be delta r? We know that, okay, delta r is the change in the radius. So this is what, this is the diameter. So you can find out whatever is like, the change in radius between 994 and 1000 divided by 2. Okay, so your delta r is going to be 1000 minus 994 divided by 2. So that gives the value of your delta r. R is going to be nothing but your 994. And here beta value is given to us. You insert all these values, you will get the answer as 500 degree centigrade, my dear students. Okay, so I hope this logic is kind of clear to everyone. I'll review it once again. What we did, we know the area of the wooden wheel. Okay, we want to see by how much we know the area of like the tire basically. So what is going to be the change in its area? Now let's say it is pi r square. So we have taken the radius as this. So dA is 2 pi r into dr. All right. So this is what I get as my differential value out here. Now A1 we saw from the previous one that A1 could be written as A plus A into beta delta t. From here we get the relation dA as equals to, or delta A is equals to A beta delta t. So here delta A could also be written as 2 pi r into delta r. So this is what I get out here, which is equal to this. All right, students. Now combining all these things together, I get 2 into delta r divided by r into beta. Delta r, whatever is the change in the radius, r is the initial, whatever the radius we are taking out here, and beta, the value is given out here. You put down the values, you get the value of delta t as 500 degree centigrade. All right, students. So this is what in nutshell is this problem. Clear? Now the next problem that we see here, these are some of the applications of thermal expansion. Okay. Now here in these, we would like to see why does the clock run slow in the summer season. Okay. It actually loses time and it gains time in the winters. All right. So why does this typically happen? We're trying to look at that. Okay. So I'll try to explain it in a fresh page. We know that during summers, the temperature rises, and as temperature rises, my dear students, okay, if your pendulum is made up of a metallic object, it is going to expand. So due to delta T, there is some delta L. Okay. Now, students, all of you are aware of this, the time period. Okay. Time period, I'll call it as, let's say, just time period here of a pendulum is given as 2 pi root of L by G. Okay, so this time period is proportional to the length. So what is going to happen in the summers? Understand this very carefully. In the summers, the length increases. If the length increases, the time period increases. Time period increases means that initially if it was taking 1 second to complete one revolution, now it is going to take a time greater than 1 second to complete the same revolution. So initially it was taking like 1 second, now probably it is going to take 1.1 second. So what impact is it going to have on the time? The time is going to run slow. Absolutely correct. Okay, the time is going to run slow out here. However, if in an examination you're not able to do these fast analysis out here, there is another method of, like, whether it's going to lose time or gain time, okay, to find that out. Okay, so students here, time period, call it as my, let's say, I'll use small t out here because capital T is referring to temperature, so small t is for time period here. So initially T1 will be 2 pi root of L by G. Now you increase the temperature by delta T, the new length has increased by delta L. So T2 is going to be 2 pi root of L plus delta L upon G. Clear, students? Now, doing it in the same page to have better continuity. So what are we going to get out here? Let me use a different color, students. Okay. So what is going to be my change in the length? Change in the length is delta t. So what is going to be the change in time? So how much time is it going to lose? Is going to be nothing but T2 minus T1. See here, the time it lost is like 0.1 second in one oscillation. So the total time it kind of lose, that we'll try to figure out. So in one oscillation out here, it's going to lose 2 pi root of G remains as it is. Okay, here L plus delta L to the power 1 by 2 minus L to the power 1 by 2. Clear? So this is the time lost. Clear, students? Acha. Now understand one thing here. 2 pi root over G. Clear? And here what do I get is I'll take my L common out here. So L comes out, it becomes like L to the power 1 by 2 plus 1 plus delta L upon L to the power 1 by 2 minus L to the power 1 by 2. Okay. All right. So here, this is what is my formula that I get, students. So calculate it carefully, 2 pi root of G. All right. And here within bracket, you will get what? Let us look at this. This is by binomial expansion, my dear students. We know that is 1 plus x to the power n is equal to 1 plus nx if x is much less than 1. And definitely delta L by L, it's going to be a very small value, isn't it? Primarily because of the fact that delta L depends on alpha, and alpha value is very less. So delta L is going to be anyways less, and delta L by L is going to be even further less. All right. So I can have this as L to the power 1 by 2, 1 plus 2 times delta L upon L, clear, minus L to the power 1 by 2. Clear. So we'll take this result to the next page, students. So we get something as 2 pi root G, all right, into, what do we get here? I think that's kind of pretty simple, and we are going to get nothing but root L, 1 plus 2 times delta L by L, root L into 1 plus 2 times delta L by L minus root of L. Clear? If you solve it further, you get 2 pi, that is the time lost or gain that we will decide out here, upon root G. You see my root L, and root L is going to cancel. I'm going to be left out with, like, root L, all right, into 2 times delta L upon L. Clear? So students, I think this is pretty clear to everyone out here now. So that it becomes my 2 pi root over G, all right, and here this will be like 2 times, there has been a slight mistake out here. Students, this is like half, so this is not going to be going into the numerator, rather it is going to come into the denominator out here. So the same logic, it was to the power 1 by 2, not 2. So 1 by 2 comes out here. So here you have got like 1 by 2. All right. And here too you have got delta L. So this is going to be like delta L and L. Okay. So here you have got like delta L upon delta root L. Okay. And you have got here 1 by 2. Okay. In a way, what we can do is we can modify this particular formula here. Half, all right. Students, here we will try to keep it as nothing, but we'll try to keep it as L, delta L by L. I'll tell you the reason why. Let's just get rid of all these things and have a very simplified version of this particular formula. So we will have 2 pi root over L by G into half into delta L upon L. Now students, we know what is your delta L equals to L alpha delta T, which implies my delta L by L is going to be alpha delta T. So I think this is pretty much sorted. Delta T, or rather out here, this thing should be equals to, what is this equals to? Original time. Okay, so original time period is equals to this. Clear? And this is like half alpha delta T into whatever is the time period, or whatever is the time. Okay, so what is this expression giving us, students? Delta T, small delta T, that it is the time lost because or gained. Absolutely, I'll tell you how. It is the time lost or gained due to the rise or the fall in temperature. Let us go ahead and do one thing. Let us analyze this formula out here. That is important. Okay, so we get a formula which is nothing but equal to delta T is equals to half alpha delta T into T. Clear? Now here, let us understand. What is this? This, my dear students, is time lost or gained. Now, time is going to be lost or gained totally depends on whether your delta T is positive or negative. So in summers, what is happening, students? In summers, delta T is greater than 0. All right. So what happens? Temperature is increasing. If temperature is increasing, my dear students, delta T is also going to increase. All right. If delta T is increasing, that means what has happened? It has actually, like, you would say it has lost time. Okay. That means the clock is going to run slow by this much. Okay. So say if your clock is running for an entire day. So in an entire day, how much time do we have? In an entire day, we have got like 24 hours into 3600 seconds. So how much time is being lost in an entire day could be given as this. And this amounts to 86400 seconds, my dear students. So the time lost or gained in summers, delta T is positive. So here, this delta T, that is my gain, or let's say loss, is going to be determined by this. So for 1 second, whatever it is, Like we saw some time back, it was 1 second for one oscillation. Now, if it is like, temperature is increasing, so this is going to take 1.1 seconds. Now, let's see. Okay, so delta T is positive in this case. So here, what is going to happen is it is going to run slow. Okay, and in the winter season, delta T is negative. So here, like, this delta T concept out here, okay, it is going to be equivalent to 0.9 seconds. So what is going to happen? Whatever used to take earlier 1 second, now it is taking 0.9 seconds. So it is going to run fast. The watch is going to run fast during the winters. And this is what is going to happen during the summers. Okay. So students, this is in nutshell or a brief about things gaining or losing time in case of your summers and winters. Is the concept clear to everyone? Okay, great. Chalo, let's proceed ahead to the next one, which is the concept of apparent expansion of solids. Okay. Now, students, what happens in this concept of apparent expansion? You've got a vessel. Okay, it's marked calibrated. All right, these are all calibrated vessels. Now, as they are kind of calibrated, my dear students, what we see is when we give heat, definitely due to volume expansion, the liquid out here is going to rise up in the vessel. Okay, so let's say it was here and it comes to this level out here. This is the final level, this is the initial level. But actually, what happens is when you heat it up, the vessel is also getting heated. So it is increasing in its dimensions as well, the vessel. So technically, it is not going to rise up to this level. It is going to rise up to a level which is greater than this level and lesser than this particular level out here. So it is going to be somewhere in between, my dear students. So for that, we use the concept of apparent expansion of liquids. So where we have your delta V is equals to V into gamma apparent into delta T. Now here gamma apparent, students, is equal to what? It is equal to gamma of the liquid minus the gamma of the vessel. So this is what you need to remember. Okay. Now, technically talking, the level of the water in the vessel could rise up, remain the same, or even come down on heating. All right. That totally depends on what is going to be the value of your gamma apparent. If your gamma apparent is positive, water will appear to rise. If your gamma apparent is 0, water is going to remain at the same level. That is, water is going to remain at this level only. No rise or fall slash fall. And if, my dear students, okay, that my gamma apparent is negative, then it is technically going to fall. All right, students. So this is what is going to happen altogether in case of a vessel containing liquid and that is being heated. Okay, so these are some of the concepts which are kind of very useful for the solving of the questions in your thermal expansion of solids and liquids, my dear students. Okay, now I've taken up a very small section along with this that is for your heat transfer. Now, as such, students, heat transfer, we have got three methodologies. It could be by conduction or convection or radiation. All right. Now, here I have taken up only the conduction process. So what happens? And it is very nice. It's kind of very interesting because of the very fact that it has got a very, very close analogy to the flow of electricity in a conductor. Okay. So here what happens is when you start heating up one end of the rod, students, what happens? The temperature of this end goes on increasing. And as it goes on increasing, there is some heat which moves in the forward direction. So this cross section out here, its temperature is also going on increasing, and so on and so forth for all the subsequent cross sections. Okay, students. Now, initially, there is going to be something called as a variable state. Now, what exactly is a variable state? A variable state is one in which the cross sections, different cross sections that we see here in this conductor, or let's say we have this, let's say, as a conductor. So what we are going to see here, that every cross section's temperature is going on increasing. All right. Now this cross section, as it is closest to the source of heating, its temperature is going to rise to the maximum. And after that, for the next cross section, then for the next cross section, and then for the next cross section. Okay, and there will be a time when there is going to be a steady state reached. Now, what happens in a steady state, my dear students? In a steady state, every cross section is going to have reached its maximum value of temperature. All right. So whatever heat that cross section is getting, say this particular cross section, whatever heat is getting, it is not increasing its temperature. It is just telling, please go ahead. So it is giving us a clear route. Okay, in the steady state, so the current flowing in the entire, the heat current flowing in the entire conductor is going to be the same, my dear students. Because before that, when it was a variable state, the heat was used in increasing the temperature. And every cross section, it's increased its temperature to a maximum value, okay, due to which a temperature gradient got created. All right. Now, once the steady state has been reached, every cross section has reached its maximum temperature, and then students, what has happened is whatever heat current is kind of coming out from here, all of it moves in the forward direction. So this is what we have out here. Is the point clear to everyone? Yes, very good. Now students, whatever this temperature gradient that got created, it is very similar to whatever we have as called as your potential difference. All right, or potential gradient which gets created at the two ends of a conductor when we have got current electricity flowing through them. So whatever we have is current electricity, here we define it as heat current. So that's like electric current. Now here we have what we call it as a heat current. Okay. Now students, if everything is same, then let's just look at the next slide out here. Okay. So we have got heat being generated. The current is flowing from A to B. This is at the positive. So this is for electrical, from the positive to the negative. Here T1 to T2, and definitely we will have T1 greater than T2. Now in case of electricity, electric current flows from higher potential to lower potential. Here, in case of heat, thermal properties, we have got heat current flowing from a region of higher temperature to a region of lower temperature. Okay. Now here, electric current was defined as delta Q by delta T. Heat current is defined as delta capital Q, that is the amount of heat transferred per unit time. That is called as your heat current. So that is like your H. Just students, very interestingly, we have studied Ohm's law. All right. So Ohm's law told us what? V is equals to IR. This is valid for your thermal conduction as well. Delta theta, this is nothing but temperature difference. This is your temperature difference. All right. Is equal to R, that is your thermal resistance, and H is your heat current. Very similar to V equals to IR. Now using all that, my dear students, what are we going to have? What we're trying to prove out here is we see delta T is going to be equal to delta T is the change in temperature. Delta theta ke badle we have taken delta T. Now we know here R is equals to what? Rho L by A, where R is what? It is called as the resistivity of the material or the electrical resistivity. Okay. We have similarly thermal resistance. R is equals to defined as thermal resistivity, okay, into L upon A. Students, I can also write this as 1 divided by thermal conductivity into L by A. All right. Same way, I can put it here. So delta T is equals to R into H. So I can put it here as L divided by Ka into delta Q upon delta T. That is my heat current. Okay. So I'm going to get delta Q by delta T, which is nothing but equals to my heat current, is equals to Ka delta T upon N. All right. Technically talking, single most important formula in this entire topic of heat transfer by conduction. Okay. So here, this is my heat current is equals to heat thermal conductivity into area of cross section of the conductor. Okay. So here, this is going to be the area of cross section of the conductor that we see here. Okay. Delta T is the change in temperature between the two ends of the conductor, and L is nothing but the length of the conductor. Okay. So students, based on this concept, I have kind of taken up two problems. Let's just quickly go ahead, look at the solution of these two problems. Okay. And then we can call it a day for today. So here what do we have? We have got two conductors, copper and steel. 75 centimeter, 125 centimeter. This end is at 100 degrees centigrade. This end is at 0 degrees centigrade. Their conductivities are given to us. Copper 386. Steel, that is iron, 46. The concept is what, my dear students? Let us understand that. There are two conductors. है ना? Very simple. These two conductors, we need to find out the temperature here at the junction. All right. So this is at 100 degree centigrade and this is at 0 degree centigrade. Okay. This is of length how much? 75 centimeter and this is of 125 centimeter. Now the basic concept you would see out here is that whatever we know is true for electrical is true for thermal. Students, can I say that these two rods are basically connected in series? Yes, they are. Okay. So if they're connected in series, then what is going to happen, my dear students? That is the current flowing through this. So call it as H is going to be equal to the current flowing through this one. All right. So whatever is the current flowing through the first rod is going to be the current flowing through the second rod. That is all the concept that I'm going to be using out here. Okay. So students, I think then it makes my life pretty simple out here. What is it? The temperature at the junction, let be at T. Okay. So we are going to get what? H as equals to 100 minus T into whatever is the conductivity, because we know the formula is delta Q by delta T, that is nothing but equals to your H is Ka delta T upon L. Clear? So delta T we have defined, K is equals to 386, all right, into area of cross section is, my dear students, because both the rods, if you see, they are joined in such a way that they have got the same area of cross section, so they have not mentioned anything about the cross section. All right, rather they have just, I can take it as A divided by what is the length, 75 centimeter. This should be equals to T minus 0, that is the temperature difference across the steel rod, into what is its conductivity, 46, into its area of cross section is the same, divided by its length is 125. So this is what we have. Okay, students, and if you kind of solve this, you will get whatever is the temperature at the junction. Okay, so if I go ahead and solve it, I'll see this A and this A is going to cancel, and I am going to have a value that is easily solvable through the calculation of this particular formula. So the basic concept was kind of important out here. That is, whatever is the heat current flowing through the first one should be equal to the heat current flowing through the second one. Okay, so students, I just leave this calculation to you people to find out whatever is going to be the temperature at the junction. Okay, so that gives us a little more time because we're coming almost very close to the end of our today's session. So this will give us a little time to our next problem. It is one of the very standard problems. And I remember this question had actually appeared for the time when I was appearing for my JEE in 2003. In 2003, this was the question which was there. And thank God I made it right during that time. Okay. So what they have asked us, they have asked us to find out the temperature at the junction. So we'll take it as capital T. Now, students, in electricity, since you're in, most of you would be in the 11th standard, you would not know exactly, like, there's something called as Kirchhoff's law. Okay. And in Kirchhoff's law, what is they are saying is that total incoming current is equals to total outgoing current. So at a junction, current will never either sink or new current is going to spring up from that particular junction. Okay. So at the junction, what we are going to see, the total incoming current, or what I can do is let me assume, or let me say, current out here is, let's say, or we will take the current coming from the higher temperature value. So let's say if I1, or let's say I is coming through this, I1 is passing through this, and I2 is going through this, then we have the concept here very simple, that is your I is equals to I1 plus I2. Now here, my dear students, this is heat current, so we are going to be like, replacing them simply by H is equals to H1 plus H2. Now what is H? H is 50 minus T. This was a JEE based problem actually. So 50 minus T, that is the thing, into whatever its conductivity is. All right. So conductivity, this is steel rod. So steel rod 50 into whatever its area of cross section. Now area of cross section for all the rods are the same. Okay. Divided by its length. Now I'm assuming that all of them are having the same length. Length is 1 meter, area of cross section is 1. So I'll just take it as L is equal to H1. H1 is this. I'm assuming now this is at a higher temperature. So this is going to be like T minus 4 into whatever its area of whatever its conductivity, that is your 400 into A divided by L plus. Okay. Students, what else do we have? Which other conductor? This conductor. Okay, so for this conductor, it is T minus 12, and aluminum's conductivity is how much? Aluminum 200 into A upon L. Clear? Students, A cancels, L cancels, which implies we have got this entire equation to find out the value of T. So 2500 minus 50T is equals to 400T minus 1600 plus 200T minus 2400. Okay, so if you kind of solve this, my dear students, what do you get? 2500 minus 600T, that is like 1900, is equals to what do we get the value of T? That is something that we can look at solving here. I think we made a small blunder. Okay, forget it. Okay, so we kind of take all these together, that is 600, and we have got another 50 coming from this side. So that is going to be your 650t, my dear students, and that all goes to this side. And here on this side we have got 2500. This side comes here plus 2400 minus 1600. So that is almost equivalent to 4900 minus 1600. So 4900 minus 1600 is going to be like this. 9 minus 6 is like 3. All right. And this is 45. Is it 49? Yeah, 49. So 49, 4 minus 1. So that is going to give me 33. Okay. So the temperature at the junction is going to be 3300 divided by 650. Students, solve it, get down the value. Okay, you will get your answer as something in decimals out here to find out whatever is going to be the temperature at the junction. But the basic concept remains the same. The basic concept is that the temperature at the junction is going to be such that the total incoming heat current is equal to the total outgoing heat current, my dear students. Okay, so I think this concept is kind of clear to everyone, isn't it? So that's all we have for today's session, my dear students. uh, so for the further sessions that we will be having in your heat, for that we need to click on this link below out here on thermal physics, and what we are going to cover in those sessions is more advanced problems on thermal heat conduction through heat transfer. This is what we are going to look at. By the heat transfer process, we are also going to take up a lot of problems on radiation, which is one of the favorite for examiners to throw questions from. So we're going to do a lot of questions on calorimetry, which we have not done, okay, in our today's session, okay, and look at one of the favorite areas, that is your heating curve, that is going to be there. So this is primarily what we are going to cover up in uh, the course that is going to be starting pretty soon. All right, it is going to be a 2-hour modular course, students. All right, in which we'll be having only numericals. Now, whatever small theory formula that I have spent quite a number of time in today's session for, like, your the time gained or lost for the pendulum clock. So probably will not be doing that in those sessions. Okay, there will be using right away. I will be giving you the formula, so I'll be just telling you, like, so the time loss was like delta t is equals to half alpha. Sorry, this is like small t is equals to delta t into your whatever is the time. Okay, so I'll give you this formula right away, explain to you whatever the meaning of these parameters out here are, and go right away to the questions. Okay, so that we will be targeting somewhere around 14 to 15 questions in a span of 2 hours, and mostly those questions are going to be your JEE based. All right, so that has appeared in your previous year's JEE examinations. Okay, the focus is going to be right now mostly mains. All right, and later in another session I'm going to take up problems which are going to be based on your advanced. So this is in a nutshell is going to be the very much the idea behind the entire course which is going to be there on thermal physics. Okay, students, I hope you enjoyed today's session, and if you want to interact after the session, what you can do is you can WhatsApp me, all right, at this number 830-880-7045. My name is Sumit Kundu, all right, and you like the video, share it, and also like it. Okay, thank you very much. God bless you all.